This time I want to talk about the higher derivatives. It turns out there are other things called the higher derivatives. What we have talked about so far, the derivative, is in this context referred to as the first derivative. Everything we've ever been doing, that's only been the first derivative. The higher derivatives are, we call them the second derivative, the third derivative. They're easy to do if you know how to do the first derivative. Here's the idea. I don't even need to say much about it. Let's say we have a function, x cubed plus 4x squared minus 7x plus 6. All right. What's the derivative? It is, you know how to do the derivative. 3x squared plus 8x minus 7, right? That's the derivative, also known as the first derivative. What's the second derivative? The second derivative is the derivative of the derivative. So to get the second derivative, you just take the derivative again, and you write that as f with two primes. This we always say f double prime. F double prime is the derivative of the derivative. So you just look here and take the derivative again. It is 6x plus 8, right? And that goes away. And if you want to, you can keep on doing this over and over again. Take the derivative again. This would be f triple prime is, in this case, just 6. And you could do even more. Now, usually people don't like to write more than 3 or so little primes. So after a while, we switch over to numbers. In parentheses means this 4 represents the fourth derivative. The fourth derivative is the derivative of that one, which is 0. The derivative of a constant is 0. And we could continue even if you want, but it's just going to stay 0 forever. If you keep on taking the derivative of 0 is 0, and it's going to be 0 forever. All right, these are the higher derivatives. They're called the first derivative, the second derivative, third derivative. The most useful of these in the real world is definitely the first derivative. The second derivative is also quite useful. The third derivative every so often comes up in the real world. The higher ones, you're unlikely to encounter them in the real world, although you can still talk about them. Mostly today, we're going to be talking about the second derivative and what it means in reality and how you use it. Let's just try another one first. How about this? Find f double prime of x for f of x equals, how about e to the power x squared? All right. Now, I gave you the original function. Actually, there is no way to just from here immediately compute the second derivative. Really, the way you do this is first you find the first derivative, and then you take the derivative again. So first, I'm going to do f prime of x is, what do you do with this? It is e to some power. So the derivative of e to some power is e to the same power again, times, because of chain rule, times the derivative of the inside, which is 2x. All right? It's usually a good idea to simplify this before you try to take the derivative again, although there's not much, ordinarily I would write this around in this order, but really it doesn't matter. 2x times e to the x squared. All right, that's the first derivative. This is not my answer. My answer is the second derivative, which I do the derivative again right here. And how do you do this derivative? This is now a product rule. We have to use a product rule. So sometimes the derivative gets harder every time. Sometimes it gets easier every time, as the case, the first example I did got simpler every time. This one actually gets more complicated every time. Anyway, we got to do the product rule. So it's going to be the first thing times the derivative of the second thing plus the second thing times derivative of the first thing. So I go first thing, 2x, times derivative of the second thing. Actually, the derivative of the second thing is the same as this, right? The second thing is the same. So we get e to the x squared times 2x for the same reasons as before. This is the chain rule. Plus, all right, that was the first thing times derivative of the second thing. Now I go to the second thing, times derivative of the first thing, which is 2. And that, my friends, is the second derivative. All right, your job was just to find the second derivative, so I'm going to leave it at that. There's no reason to simplify this unless I ask you to do, some other stuff, which I didn't. Let's talk about what this is useful for. So f double prime, let's just talk about the second derivative for now. This measures, if you think of this as a rate of change, what is it? It's the rate of change of the rate of change, right? It's the derivative of the derivative. Another way to say that, measures, f double prime measures how quickly f prime is changing. It's the rate of change of f prime. Is that useful for anything? Actually, it is. This is something that people talk about all the time. If f prime itself already has a meaning, then f double prime has an interesting meaning. Here's an example. So in physics, with the motion of objects, if I have an ordinary function, f of t, measuring the position of an object, what does the derivative represent? Then f prime of t is the velocity, right? How fast, it's the rate of change of the position, how fast the position of the object is changing. That means the velocity, right? The speed of the object, right? Then what is, that's then. Then f double prime of t, there's a word for this that everybody knows. This is a very common concept. This would mean how fast is the velocity changing, right? It's the rate of change of f prime, but f prime is the velocity. So f double prime is how fast is the velocity changing. There's a word for that. That's called the acceleration, right? The acceleration. This is the second derivative. So in physics, the second derivative, physics describing motion of objects, the second derivative represents the acceleration, which is super important in all kinds of situations. The second derivative also has meaning in other contexts. Here's a financial context in which the second derivative has meaning. How about this? Here's a financial type example. If f of t is a function which describes the value of money, this is a little abstract, but as you know, money itself changes its value over time. Like $1 today is worth considerably less than $1 100 years ago. And this is because of inflation, right? The value of money changes over time. So if f of t represents the value of money, then f prime of t is the rate of change of the value of money. That is how a measurement of how the value of money is changing over time. Actually, that's called the inflation rate. F prime of t measures inflation, or deflation, I guess. Inflation means the value of money is decreasing, f prime of t being negative in that case would mean inflation is occurring. F prime of t being positive means the value of money is increasing, which in the real world doesn't usually happen. That's usually a sign of problems in your economy if deflation happens. Anyway, f prime of t measures inflation. What about f double prime of t? F double prime of t is how fast inflation is changing. All right. So every time some politician says, hey, since I've been the president or whatever, inflation has slowed down, what they are telling you is something about the second derivative of something. They're saying the rate of change of the inflation has decreased. But the inflation itself is a rate of change of the value of money. So this is another case in which the second derivative has some kind of real world meaning. And there are many, many other examples. I'm just trying to give you a little flavor for it. There's another style of notation that we use. When you write your function as f of x, the derivative is written f prime of x. You may have seen every so often, I don't usually write this way, but every so often you will see, instead of f of x, if you write your function called y, then the derivative is called dy dx, written in this way. How do you write the higher derivatives in this format? So, like we said, the second derivative is f double prime. I write it that way. In this style, the way you write the second derivative, this is a little weird, and I don't really want to get into it, but the way you write the second derivative in that style is like that. D squared y dx squared. It's because you think of this as d dx of y, the derivative of y. This one you would think of the derivative of y, right? And you put these d's together, you get d squared. You put these dx's together, you get dx squared. That's why it's written in this slightly weird way. The third derivative of x would be written d3y dx to the third, right? So this is just, if you see these things, they mean the higher derivatives. They're written in a slightly strange way. Let's talk about what do the higher derivatives look like on a graph. Everybody knows the first derivative represents the slope at each point. Can you sort of look at a graph and eyeball the second derivative? Actually, you can. Let's try it. It's not so easy actually to eyeball a graph and say as a number what the second derivative is, but you can definitely identify on a graph if the second derivative is positive or negative. Let's just think about what this would mean. What does it look like when the second derivative is positive? What it means, first of all, this means that the rate of change of the first derivative is positive. Another way of saying that is the first derivative is increasing because its rate of change is positive, which means increasing. So this means f prime is increasing as we move to the right on the graph. This means that f prime is increasing as we move to the right on the graph. What would that mean? What would that look like? It could look like something like this. How about this, right? Here we have f prime, remember, represents the slope. It means here the slope is very small, close to 0, but it is increasing as you move to the right. Okay, so this picture is one in which f double prime of x is positive because the slope starts off pretty close to 0, but it gets increasing as we move to the right. Another way this could happen is like this. In this case, the slope is super negative and becoming less negative. That also counts as an increase, right? If you have a number which is super negative and it becomes less negative, that number has increased. So both of these pictures represent an increasing of slopes as you move from the left to the right. Or if you want to sort of put it all together, something like that, right? This is starting off negative, then becoming like 0, and then continuing to increase to a positive. So when I see f double prime of x positive, it tends to have this kind of shape. All of these shapes are ones which you can make with your hand sort of faced that way, right? And this kind of measurement of the shape of the graph is not the slope, because the slope is different for all these. Like this has a negative slope, this has a positive slope. It's how the slope is changing. It's not called slope, it's called concavity. So we say this one has positive concavity, is the geometric way to describe the second derivative being positive. Sort of the shorthand is we just say that f is concave up in all of these cases. So f double prime greater than 0. The words we use to describe this situation is concave up. And such a thing, concave up, means it looks like this, right? The curvature, the curvaceousness has this shape to it. It's like that, right? It's the smiley shape, all right, without the eyes. The smiley shape means concave up. What does it look like when the derivative is less than 0? The second derivative is what I'm talking about. I said derivative. I meant the second derivative. What does it look like when the second derivative is less than 0? This is called concave down. And instead of that way, is that way, right? It's the frowny rather than the smiley. The frowny shape is called concave down. So it could look like that, or it could look like that, or it could look like that, right? All of these shapes are concave down. What that means is the slope decreases as you move to the right. Check it out. This one, the slope is quite steep here, but becomes less steep. So the slope is very positive and then not so positive anymore. That means the slope is decreasing. Here also the slope is close to 0, but then it becomes negative. That means the slope decreased. And the same thing happens here. Throughout this whole picture, the slope is decreasing. Here it's quite positive. Here it's quite negative. So this is what concave down looks like. It looks like this way around, right? So this shape is concave up, the smiley. This shape is called concave down. And those are measurements of the sign of the second derivative. Second derivative being positive means concave up. Negative means concave down. Now, most of the time, the graph you're looking at doesn't look like one of these. It has some kind of combination or mixture of both concave ups and concave downs. Let's check it out. All right, how about this picture here? I would like to look at the picture and I want to give intervals where it's concave up and down. You know, this is something we did in previous sections about increasing and decreasing, was about the slopes, where the slope's going up versus where the slope's going down. This time I want to do the same thing, but not about the slopes, about the concavity. You should be looking at this picture and trying to identify where exactly does it have that shape and where does it have that shape. And you can see, sort of informally, the uppity part would be around here, right? This is the smiley part, so that's where it's concave up. And the frowny part would be around here and around here, all right? There are special sort of individual points in between here where it switches from being smiley to frowny. I would say somewhere around there, maybe. I tried to make that line up with this x equals 2. And somewhere around here is another point where it switches from being a smiley to a frowny, all right? And there are names for those. In the first derivative, the place where the slope switches from being positive to negative, those are the critical numbers, those are the relative extrema. In the case of the second derivative, there's a name for these points. These are called inflection points. Inflection points. These are points. Inflection points are the points where f double prime changes its sign. So here, the second derivative is negative because it's frowny. But at this point, it switches to becoming positive. And then at this point, it switches to becoming negative again. All right, can we just say the answer here? Give the intervals where the function is concave up versus down. Okay, so it's up on the smiley pace. Concave up. On the interval, that would be here, 2 to 4, right? And it's concave down. On the interval, so there's this one here, which goes 4 to infinity. Sorry about my squeaking. And this one over here, minus infinity to 2. There you go.